Alright, welcome everybody. So today I'm going to talk to you about hybridization. Before I do that though, I wanted to just briefly run through some properties about different kinds of substances. So these are important for you to memorize and know. The first one is an ionic substance. This is obviously where you would have ionic bonding. If you have an ionic substance, it conducts electricity when it's a liquid or when it's dissolved in water. They generally have high melting points and boiling points, and they're soluble in water. Now, the reason why an ionic substance can conduct electricity in water is because these ions that make up the ionic solid. So if I draw them like this, as a solid, they're linked together. They're static. They can't move. But when they dissolve in water, those ions now are free to move around. So this would be my solid form. This would be my aqueous form or my liquid form if I melted them. So if you're polar, you can also conduct an aqueous form if you are an acid. So if you're an acid like HCl or even acetic acid, depending on how strong the acid is, will depend on how many ions you form and will depend on how well you conduct. Polar molecules tend to have lower melting points and boiling points. For example, if we were to look at something like water, it has a melting point of around 0 degrees Celsius. A melting point of an ionic solid like, NaCl is about 900 degrees Celsius. And then you have substances that are non-polar. So these don't conduct electricity at all when they're, either dissolved in water or if they do dissolve in water, which they generally don't, or as liquid forms, or even as solids, they don't conduct. They tend to have very low melting points and boiling points, and they are also insoluble in water. So we'll talk about why this is the case, especially with the melting points and boiling points, and it comes down to something called intermolecular forces, which we'll actually do in the next video. Alright, so let's talk about orbitals hybridization. So, before an atom bonds, it has its own orbitals for its electrons. For example, if we take something like carbon would be 1s2, 2s2, 2p6. Now what happens is when these atoms bond, especially an atom that is central, bonded to many other atoms, 2, 3, 4, 5, 6 atoms, the orbitals that originally were there, they'll start to mix and they'll overlap. And they will actually turn into a new shape and have a new energy. That's really all that hybridization is. If you look at it conceptually, if you're not getting into the details, which we'll do in a second, what you need to know really is that the orbitals from the atoms, they're bonding together with other atoms, and in doing so, those orbitals are changing shape, they're changing energy. The idea is, we have to account for these shapes that we see with Vesper. The hybridization that occurs will explain this. So the term hybridization means, again, to just mix the orbitals together. They're going to have new characteristics, so they're going to have different shapes, and you'll see those on the next page, and they're also going to have lower energy. Now something important is that, like if I were to take, 4 orbitals that were originally present in the atom that I'm hybridizing, and I were to have 4 electrons in those orbitals, when I mix them, I'm still going to have 4 orbitals, I'm still going to have 4 electrons. The only thing that's really changed is the shape. So the shape and the energy of the orbitals. So let's take an example that I really like, which is CH4, which is methane. And so when we look at CH4 here, we have a carbon in the middle. So here's my carbon, and it's bound to 4 H's. So I have my carbon bound to 4 H's. Now if I look at carbon before bonding, so we'll do BB before bonding, the valence electrons are 2s, like this, with its 2 electrons, and 2p, which has 3 orbitals like this, and 2 electrons. Now I can look at the shapes of these too. So if I look at the shapes of s, the s orbital looks like this, it's circular, and the p orbitals, they have these lobe shapes to them like this, if you remember from the previous chapters that we did. So now they're going to mix together to form this tetrahedron. The number of domains that are needed to form a tetrahedron is 4. So I'm going to try and mix together 4 orbitals. So I'm going to mix together these 4 orbitals. So we're going to mix together s and 3 of the p orbitals. And we're going to create 4 new orbitals. 1, 2, 3, 4. Now these orbitals have a new name because I mixed together an s orbital and I mixed together 3 p orbitals. I'm going to have sp3. That is where the name comes from. It just comes from the fact that you mix together 1 s and 3 p's. Now those electrons, they're going to follow Hund's rule in these orbitals, and they're going to each take up their own orbital to minimize repulsion, and the shapes of the orbitals are going to be different. The shape of the first orbital is going to be like this, and every other orbital is going to be identical. And it's going to look like this. And these are going to be my 4 hybrid orbitals. Now what I can do with these is I can arrange them in a tetrahedron to minimize their repulsion. So we'll have one of the orbitals like this, one like this, one like this, one like this, each of them containing an electron. This is my carbon atom hybridizing. Now if you don't like my drawings, I know that they're pretty, but I can show you what this looks like on this page right here. Here it is. Here's my isolated carbon atom on the left here. Here they mix together. The 4 orbitals, 1, 2, 3, 4, mixed together form 4 new orbitals called sp3. All of the electrons are in separate orbitals. They're mixed together like this. This is what the shape looks like. This is my sp3 hybridized carbon. If I look at something like boron, I didn't explain this to you before, but when we look at boron and why it takes the shape it does, why doesn't boron form a double bond? Why does it only form 3 bonds? I didn't really talk about the hybridization, but that's why it does it. When we look at boron in the middle here, boron started off with 2s2, 2p1, that was the electron configuration, so it had 2s and 2p. It's going to bond to the 3f atoms, so it's going to mix together 3 p orbitals. So it mixes together these 3 p orbitals. One of the p orbitals isn't hybridized, it's left there, it's empty. But we can see that now we have this sp2. We could go to sp and sp3d and sp3d2, I'll show you in a second. But this is just showing you, like from an AP textbook, here's our original orbitals before they actually hybridized. Here they formed the hybrid orbitals, so they mixed together. Here they are hybridized in 109.5 degrees. Now, here's another set of hybrid orbitals, both sp3, but this one's for NH3. So N in the middle, it is 2s2, 2p3. It's going to form 3 bonds with H, and it's going to have 1 lone pair. So it's going to have a total of 4 domains. So now I mix together 4 orbitals. But notice here, one of the hybrid orbitals is actually a lone pair. And that's what happens. It doesn't have to be a bonded atom to be hybrid. It could be a lone pair that's hybridized too. And so here I have my NH3, and it's hybridized, and we have one of the lone pairs being hybrid. Here we have H2O. So H2O, we have the O in the middle hybridizing. That's 2s2, 2p4. So those are my electrons here. Again, 4 domains, 2 bonded, 2 non-bonded. So we're going to mix all 4 orbitals, except 2 of them are lone pairs. So lone pair hybridized, bonded hybridized, bonded hybridized. So this just goes quickly through how they mix together the orbitals. What if I have an expanded octet? What if I were to have something with d orbitals? Well, here's phosphorus, and it is forming PCl5. So phosphorus needs to hybridize 5 orbitals. So it hybridizes its s orbital, it hybridizes 3 of its p orbitals, and it hybridizes a d orbital. It mixes them together to form 5 sp3d orbitals, each with a single electron following Hund's rule. And what we end up with PCl5. What if I wanted to form 6 bonds? I need 6 domains down here. So 6 domains, here I go. We have 1 orbital, 3 is 4 orbitals, and 2 more, 5 and 6 orbitals. I mixed them together. I mixed an s orbital, I mixed together 3 p orbitals, and I mixed together a d orbital for a total of 6 orbitals, each one with 1 electron. Now, if you want a quick way to go through and well, how do I know this? You could go back to the chart here, back to the chart here, and you could use the geometries. If you are 2 domains, you will always be sp. You'll mix together 2 orbitals. If you are 3 domains, whether it's a lone pair or not, you'll be sp2. If you are 4 domains, you'll need 4 orbitals, sp3. If you are 5 domains, you'll need 5 orbitals, sp3d. And if you are 6 domains, you will need 6 orbitals, sp3d2. Okay, so there goes my hybridization. Really, the AP exam only really asks you to identify how many hybrid orbitals there are in a given molecule. There's been some recent findings that say that the sp3d and sp3d2 are not what exist, and so there's some controversy about that that's brewing. So they actually took that out of their curriculum. But I still teach it to you. There is still evidence that shows that it is valid. Okay, the last thing I want to talk to you about before we stop this video is sigma and pi bonds. And what a sigma and pi bond is, it shows you the type of bond that occurs. If we have a single bond here, and I show this with NH3, and here's the hybrid orbitals, each one of these parts right here, that is one of the sp3 orbitals. Well, it is bonding to an H that has an unhybridized orbital there. That end-to-end overlap between the orbitals when you have a single bond is called a sigma bond. And so a sigma bond is an end-to-end overlap of orbitals. So whenever you have a single bond, the overlap's always end-to-end. And so these 3 bonds right here, this would be a sigma, this would be a sigma, this would be a sigma. We'd have 3 sigma bonds here. But what if I have something with a double bond? Well, if I have something with a double bond, then what ends up happening is one of the bonds isn't hybridized. So this shows you down here C2H4. C2H4, it has a sigma bond here. It has let me change this to white. It has a sigma bond here, end-to-end overlap, sigma bond here, sigma bond here, sigma bond here, sigma bond here. But the p orbitals, they also have electrons in them. They're not going to have this end-to-end overlap. Instead, they're going to have a side-to-side overlap, and they call this a pi bond. A pi bond is a side-to-side overlap. A sigma bond is an end-to-end overlap. And so when I look at something like C2H4, the C is hybridized as, or the C starts out as 2s2, 2p2. So it has 2s, it has 2p2. Now, when this hybridizes, when I have my C double bonded to my other C, it's not writing well for some reason. Let's move this down. So I have my C double bonded to my other C like this. What I notice is that one of the bonds here is hybridized, and that's the bond right here. The other bond is not hybridized, and that's the bond up here. So when I have my trigonal planar geometry, my carbon is sp2 hybridized. That means that it mixed together an s and 2p. But it left out one of the p orbitals that did not hybridize. That p orbital will have an electron in it. That electron will form a pi bond. What you really need to know for sigma and pi bond is the type of bond that forms when you have a side-to-side overlap as a pi, and when you have an end-to-end overlap as a sigma. You should also know that if you're single, you will have one sigma.
Oh, okay, yeah, I'll have it in here. So
hold on a second, please. Bond, you will have one sigma, When you have a double bond, you will have one sigma and one pi. One of them will be an end-to-end overlap. One of them will be a side-to-side overlap from the p orbital that did not hybridize. And when you have a triple bond, you'll actually have one sigma and two pi bonds. Now, this is my hybridization and the sigma and pi bond, what you need to know. So thank you for watching, and we'll talk about this in class. Thanks so much.